Hi. It's been a while, but it's great to see you back at Dr. S's Random Math Lair. Today's video features problem 9, and it's about how to describe a parabola in terms of what is known as its standard form equation. A parabola is a type of conic section, such as an ellipse, which was discussed in the video for problem 6. We shall talk a bit more about this idea subsequently. The topic of this video is quite frequently covered in geometry, algebra, pre-calculus, and elementary calculus courses, typically at the high school senior or college freshman level. Before solving problem 9, we shall discuss the historical background and real-world applications of parabolas. Links to some important online resources will also be provided at the end of this video, and in its description. Here's the statement for problem 9. For part A, given the equation x plus 4 whole squared, equal to negative 2 times y minus 1, written in the standard form, determine the vertex, focus, directrix, and axis of symmetry of the parabola it represents. Next, for part B, write the equation from part A, in the quadratic form y equal to ax squared, plus bx plus c, where a, b, and c are real constants. Finally, for part C, find the equation of the parabola with focus at the point 2, negative 2, and y equal to 4 as the directrix, in the standard form. The terms standard form, vertex, focus, directrix, and axis of symmetry will be defined in more detail subsequently. Now one may ask, what's the big deal about parabolas anyway? Well, for starters, parabolas are a type of conic section, a curve that one gets by intersecting the surface of a right circular cone with a plane. Recall from the video for problem 6 that we mentioned ellipses and hyperbolas also as conic sections, with circles being a special case of ellipses. We shall work with hyperbolas in a future video. In particular, if the plane intersecting the right circular cone is parallel to the edge of the cone, then the resulting unbounded curve is a parabola, as in image number 3 in the given picture of conic sections. Note that even a right circular double cone can be used to demonstrate and describe the different types of conic sections. Now we are ready to explore some of the historical background of parabolas. A bit later, we will also discuss some real-world applications of parabolas, before going ahead and solving problem 9. Now let's explore the historical background of parabolas. The study of conic sections, including the parabola, is said to have begun in ancient Greece around the 4th century BC. This map depicts Greece somewhere in that time period. In particular, it shows the Greek city-states under the control of the city of Thebes. Known as the Theban hegemony, this was the age when Thebes had defeated Sparta, well after the Peloponnesian War roughly a century prior, primarily between Athens, Sparta, and their various allies. Here's some more historical background on parabolas. In the 4th century BC, the Greek mathematician Menaechmus, a student of Plato and Eudoxus, studied the parabola, ellipse, and hyperbola as conic sections. Toward the end of the 4th century BC, and the beginning of the early 3rd century BC, Euclid of Alexandria wrote about the parabola, and by the late 3rd century BC, Apollonius actually became responsible for its present name. By the time Greece had reached the 3rd century AD, Pappus studied the focus and directrix of a parabola. These terms will be defined in more detail shortly. With the advent of the European Renaissance, Galileo showed that projectiles travel in parabolic paths, around the 16th century. Newton, about a century later, considered the properties of the parabola that bring parallel rays of light to a focus. Centuries later into the modern age, parabolas are still widely used in a number of real-world applications, as we shall see next. The sources for the above images will be provided at the end of this video, and in its description. Now let's look at some applications of parabolas in our daily lives. Apart from just math, parabolas have a vast number of real-world applications. This includes areas in engineering, physics, and the natural sciences. Here are just a few examples of such applications. Parabolic reflectors are used in automobile headlights, telescopes, microwaves, and satellite dishes. Parabolas are also used in architecture, for instance, in suspension bridge cables as in San Francisco's Golden Gate Bridge, and in arches such as those in Japan's Twin Arch 138. In ballistics, parabolas are used in approximating a projectile's trajectory. Experimental aircraft, like NASA's Vomit Comet, have the ability to travel in vertically parabolic trajectories periodically, giving a zero-gravity effect. Water fountain jets can take on a parabolic shape. As a final example, in certain sports, a ball struck in the air travels in a parabolic path. The sources for these images will be provided at the end of this video, and in its description. Before we move on to solving problem 9, we shall next consider the geometry of parabolas, followed by some quick facts and review. Parabolas are intrinsically geometric objects, so it makes sense to discuss their geometry. In math, a parabola is a plane curve shaped like a U, living in the xy plane, with mirror symmetry. It can also be described by a point called the focus, and a line called the directrix, such that the focus doesn't lie on the directrix. A parabola is then defined as the locus of points equidistant from both the focus and the directrix. The line perpendicular to the directrix and passing through the focus is the parabola's axis of symmetry. The point where the parabola intersects its axis of symmetry is its vertex. The distance between the vertex and the focus along the axis of symmetry is called the parabola's focal length. The chord of the parabola parallel to the directrix, and passing through the focus, is called the latus rectum of the parabola. Figure 1 visually sums up this geometrical description of a parabola, in particular one that opens upward. In fact, parabolas can also open downward, to the right, or to the left, depending on certain conditions, as we shall see in the quick facts and review needed to solve problem 9. Let's begin with some quick facts and review we will need to solve problem 9. These in particular are typically taught at the high school level. A parabola with a vertical axis of symmetry has equation y equal to ax squared plus bx plus c, where a, b, and c are real constants. This is a quadratic equation, and is referred to as the equation of a parabola in quadratic form. Sometimes certain high school textbooks call this the equation of a parabola in standard form, but we shall not do so. If a is strictly positive, then the parabola opens upward, and if a is negative, then the parabola opens downward. In particular, this parabola's axis of symmetry is given by the equation x equal to negative b over 2a, so that its vertex is given by the following point. This parabola has a y-intercept given by the point 0c. Recall that the video for problem 4 showed how to find the y-intercept for a line in the slope-intercept form. The same idea can be applied here by simply setting x to 0, which gives a y-coordinate of c. The existence of x-intercepts for this parabola depends on the quadratic formula, where d denotes the discriminant, b squared minus 4ac, of the parabola. If d is negative, there are no x-intercepts. If d is 0, there is only one x-intercept, and if d is strictly positive, there are two x-intercepts. A similar analysis can be done for a parabola with a horizontal axis of symmetry. Note that the quadratic equation is now x equal to ay squared plus by plus c. In this case, a strictly positive implies that the parabola opens to the right. However, a negative implies that the parabola opens to the left. We continue with some more quick facts and review for problem 9. These are more advanced than at the high school level. Let's consider parabolas with vertex hk, given by the origin 0, 0, first. The standard form of this type of parabola, with a vertical axis of symmetry, in this case the y-axis x equals 0, is given by the equation x squared equal to 4py. In this case, we have the following. If p is strictly positive, the parabola opens upward, while if p is negative, the parabola opens downward. Its focus is given by the point 0p, and its directrix has equation y equal to negative p, as shown in figure 2. For the other case, where the parabola has a horizontal axis of symmetry, that is, the x-axis y equals 0, the standard form equation is y squared equal to 4px. In this case, if p is strictly positive, the parabola opens to the right, while if p is negative, the parabola opens to the left. Its focus is given by the point p0, and its directrix has equation x equal to negative p, as shown in figure 3. Note that in both cases, the absolute value of p designates the focal length of the parabola. The source for these figures will be given toward the end of this video, and in its description. Here's the last set of quick facts and review for problem 9. Now consider parabolas with vertex hk, in general. The standard form of this type of parabola, with a vertical axis of symmetry, in this case the line given by the equation x equals h, is the equation x minus h whole squared equal to 4p times y minus k. In this case, we have the following. If p is strictly positive, the parabola opens upward, while if p is negative, the parabola opens downward. Its focus is given by the point h, k plus p, and its directrix has equation y equal to k minus p, as shown in figure 4. For the other case, where the parabola has a horizontal axis of symmetry, that is, the line given by the equation y equals k, the standard form equation is y minus k whole squared equal to 4p times x minus h. In this case, if p is strictly positive, the parabola opens to the right, while if p is negative, the parabola opens to the left. Its focus is given by the point h plus p, k, and its directrix has equation x equal to h minus p, as shown in figure 5. Once again, in both cases, the absolute value of p designates the focal length of the parabola. The source for these figures is the same as for figures 2 and 3. It will be given toward the end of this video, and in its description. Now let's begin solving problem 9. For part A, we have the given equation x plus 4 whole squared, equal to negative 2 times y minus 1, which we label as 9.1. This is the equation of a parabola with a vertical axis of symmetry, in standard form. Clearly, its vertex is the point negative 4, 1. From the standard form, we see that 4p equals negative 2, implying that p equals negative 1/2. Since p is less than 0, this parabola opens downward, and corresponds to the rightmost parabola from figure 4. Then, using figure 4, we have that the focus is given by the point negative 4, 1/2. Moreover, the directrix has the equation y equal to 3/2. It's easy to see that the axis of symmetry has the equation x equal to negative 4. Here in figure 6, this parabola is outlined in solid black, its vertex is in black, its focus is in red, its directrix is in green, and its axis of symmetry is dotted. Notice that its focal length, in this case the vertical distance between the focus and the vertex, is then given by the absolute value of p, which is 1/2. We continue solving problem 9, this time considering part B. Now let's go back to the original equation from part A, given by 9.1. Part B asks us to rewrite the above as a quadratic equation of the form y equal to ax squared, plus bx plus c, which we label as 9.2. We start by expanding both sides of the original equation from 9.1, which gives us x squared, plus 8x plus 16, equal to negative 2y plus 2. Rearranging the terms above, we obtain the following in 9.3. Dividing both sides of 9.3 by negative 2, we get the quadratic equation y equal to negative 1/2 x squared, minus 4x minus 7 in 9.4, solving part B of this problem. Note that in view of 9.2 we have a, equal to negative 1/2, b equal to negative 4, and c equal to negative 7 in 9.4. Plugging a, b, and c into the quadratic formula, we get the x-intercepts of this particular parabola, given by the points negative 4 plus or minus the square root of 2, 0. The value of c gives us the y-intercept of this particular parabola, that is the point 0, negative 7. Moreover, the discriminant d equals 2, which is strictly positive and justifies the existence of exactly two x-intercepts. I encourage you to verify these facts as a simple exercise. Let's finish solving problem 9. For part C, we are given a parabola with focus at the point 2, negative 2, and directrix given by the equation y equal to 4. We have to find its standard form equation. The directrix being above the focus means the parabola must open downward, corresponding to the rightmost parabola in figure 4. This occurs only if p is negative. The axis of symmetry is given by the equation x equal to 2, and clearly the point 2, 4, lies on the directrix. Let's denote the vertex of the parabola by the point 2, k. Now the focal length, the absolute value of p, is also the distance from the vertex to the point 2, 4, on the directrix, since a parabola is the locus of points equidistant from both the focus and the directrix. So the distance from the focus to this point is twice the focal length, that is 2 times the absolute value of p, which is computed as 6, and this implies that the focal length is 3, so that p equals negative 3. I leave you to verify this using the distance formula. From figure 4, the equation of the directrix tells us that k equals 1. So the vertex is the point 2, 1, and 4p equals negative 12. Therefore the standard form equation for this parabola is x minus 2 whole squared, equal to negative 12 times y minus 1. Here figure 7 uses the same exact color coordination as in figure 6.